In this lecture, we'll discuss the entropy change of an isolated system when it undergoes an irreversible process. That is, we are going to look at the second part of the second law, which you recall states that in a real process, entropy of an isolated system always increases. Now, we are going to give a proof of this statement, and by proof, we mean that we are going to reduce this statement that during an irreversible or real process, the entropy of an isolated system increases. We are going to reduce this statement to a simpler statement, such as the Clausius statement. So, to show this, that is to give the proof of the second part of the second law, we're going to again consider two heat engines. So we'll consider engine E and E prime. But unlike our previous discussion on showing that the efficiency of a Carnot engine is independent of the working substance, where we consider two reversible heat engines E and E prime, in this case we are going to consider two different type of heat engines. So engine E we'll consider to be reversible and engine E prime we'll take to be irreversible. So what we have is we have these two thermal reservoirs, let's say at temperature T1, at temperature T2, and we have these engines that operate in a cycle, which are E and E prime, and both of these engines work within the same temperature difference, that is between same thermal reservoirs at temperatures T1 and T2. Now engine E is reversible. That means we can run that engine in the opposite direction, that is in the opposite cycle. Therefore it can operate as a refrigerator. That means, let's say this engine E takes in heat Q2 and rejects heat Q1 to the high temperature reservoir, and this engine E prime is irreversible and it operates as a heat engine. So let's say in general it takes heat Q1 prime and rejects heat Q2 prime while delivering work, and that work is fed into this refrigerator, that is engine E, working in reverse. And this work from the first law is Q1 prime minus Q2 prime. Let's first consider that the efficiency of this engine E prime, which is the irreversible engine, is greater than the efficiency of the reversible engine E. So eta prime is greater than eta, and because the work output of engine E prime and the work input of this refrigerator E are the same, what we mean by this inequality is that W over Q1 prime is greater than the work done by the engine E if it was operating as a heat engine. So that means Q1 is greater than Q1 prime. And this is because we've taken the efficiency of the engine E to be smaller, so to do same amount of work, engine E is going to take in more amount of heat from the high temperature reservoir. Now, using the similar logic that we have seen earlier, what we are going to do is we are going to look at this combined system of heat engine E prime and refrigerator E, that is engine E working in reverse because it's a reversible heat engine. So again, as we've seen earlier, what we get is A system that operates in cycle does not consume work but takes in heat Q2 minus Q2 prime, which from the first law is equal to Q1 minus Q1 prime, and we've shown this in one of the previous lecture where we showed that the efficiency of the Carnot engine is same irrespective of the working substance, and this heat is Q1 minus Q1 prime. So therefore, starting with this assumption, we arrive at this picture over here where we have a device that operates in a cycle and it consumes no work, but it is transferring heat from a low temperature reservoir to a high temperature reservoir. So clearly this is not possible. It's a violation of the Clausius statement. Therefore, we can say that this statement is not possible. Similarly, we can also exclude the possibility of efficiencies of both of these engines to be same, because E prime is irreversible, and this holds only for reversible engines E and E prime. Therefore, we can rule out this possibility. So what we are left with is that the efficiency of the reversible engine E must be strictly greater than the efficiency of the irreversible engine that is operating between the same high and low temperature reservoirs. Therefore, to deliver same amount of work, the heat absorbed by the irreversible heat engine is higher than the reversible engine. That is, Q1 prime must be greater than Q1, because to have same amount of work delivered by the engine, the more inefficient engine, that is engine E prime, has to take in more amount of heat from the high temperature reservoir. And one thing to note is that unlike our earlier discussion where we showed that the efficiencies of the Carnot engines are equal, in this particular case, we cannot have a situation where engine E prime is running in reverse as a refrigerator, because engine E prime is irreversible. So the only way we can have a refrigerator is to operate this engine E in reverse, and engine E prime cannot run as a refrigerator. Therefore, we must have eta greater than eta prime. So because we have this efficiency of a reversible engine is greater than efficiency of an irreversible engine, we can also write 1 minus eta prime must be greater than 1 minus eta. And note that what is this 1 minus eta prime is because efficiency is 1 minus Q2 over Q1. So 1 minus eta is Q2 over Q1, and this is for the irreversible engine, and this is greater than Q2 over Q1. And we've seen in one of the previous lectures that for a reversible heat engine, Q2 by Q1 is equal to the ratio of the absolute thermodynamic temperatures of the reservoirs. So it is equal to T2 by T1. Therefore, we can write this equation as Q2 prime over Q1 prime, that is the heat transferred between the irreversible heat engine with the corresponding thermal reservoirs, is greater than T2 by T1, which are the temperatures of the thermal reservoirs. This inequality can alternatively be written as Q1 prime over T1 minus Q2 prime over T2 is less than 0. So if now we consider a heat engine that absorbs and rejects infinitesimally small amount of heats and operates on a cycle that is partially or fully irreversible, then we can write for a heat engine which takes in infinitesimally small amount of heat, and this is an irreversible heat engine, so I've put primes over here. Note that here T1 and T2 denote the temperatures of the thermal reservoirs and not that of the system. So now if we have an arbitrary heat engine which takes in finite amount of heat and rejects finite amount of heat from thermal reservoirs at different temperatures, then following the same approach of subdividing a cycle into infinitely many cycles for an arbitrary cycle which is fully or partially irreversible. So we can have many such heat engines which take in infinitesimally small amount of heat, and these are irreversible heat engines. So if we sum up all such contributions, what we get is dq prime by t, and integral over the whole cycle which is fully or partially irreversible must be strictly less than 0. And note that in this sign convention we have that dq prime must be positive, it is added to the system, and dq prime is negative if we take away heat from the system. It is important to note that the temperature T in this inequality is not the temperature of the system. It is the temperature of the thermal reservoir that is supplying heat dq prime to this system. And this is because we have arrived at this inequality starting with this simple inequality for one heat engine, that is dq1 prime by t1 minus dq2 prime by t2 is less than 0, and there t1 and t2 are the temperatures of the thermal reservoirs with which this heat engine exchanges heat, and therefore in this inequality temperature T is the temperature of the thermal reservoir with which this heat engine exchanges heat. So now that we have this inequality, let's consider a system that undergoes this cycle. So on a PV diagram, we have a system that can be between states 1 and 2, and it can go from state 1 to state 2, let's say through an irreversible process, and it goes back from state 2 to state 1 through a reversible process, and that's why we've shown it in a continuous line. So this cyclic integral is equal to first over this irreversible process going from 1 to 2 and 2 to 1, which is a reversible process. So let us explicitly state that over here, that is, this is reversible heat addition to the system during the process 2 to 1, and we know that this should be strictly less than 0 because our overall cycle is irreversible. Now recall that this term over here, this integral, is the difference in entropy at state 1 and state 2, because in the previous lecture we have defined that the entropy change is given by this integral, that is dq reversible over the absolute thermodynamic temperature and integral of that. So what we get from here is S2 minus S1 is greater than dq prime over t, and this is integral over 1 to 2. And this dq prime, note, is the heat that is being added to the system during this irreversible process. Now, this inequality applies to any kind of system undergoing a real irreversible process. This inequality takes a simple form if we have an isolated system, and for an isolated system there is no heat transfer to the system from the surroundings, and therefore we can conclude that S2 minus S1, which is greater than this integral, would be greater than 0, because this integral would be exactly equal to 0 for an isolated system, because there is no heat transfer between the isolated system and its surroundings. In other words, what we see is that for an isolated system which is undergoing an irreversible process, S2 is always greater than S1, and it is strictly greater than S1. That is, entropy of an isolated system can only increase during a real process which is an irreversible process. Therefore, the second law provides a definite direction to the process that can occur in reality, something that first law is unable to predict. So first law says that if you have a process, let's say an irreversible process that an isolated system is undergoing, it may go from state 1 to state 2 or state 2 to state 1. It does not predict in which direction this system is going to proceed. But the second law is able to predict the direction. So the isolated system will evolve in a direction where its entropy is going to increase. So we can now generalize our discussion of the first and second part of the second law. So if we combine the discussion of the previous lecture and this lecture, what we can write is that we have, in general, for the cycle, we have this inequality that dq by t, an integral over cycle, is always less than equal to 0, and equality holds strictly for a reversible cycle. So this inequality is called the Clausius inequality. And from this inequality, we can say S2 minus S1 is always greater than equal to where the equality holds again for the reversible process. And finally, from this equation, we get that for an isolated system, S2 is always greater than or equal to S1. That is, the final state has an entropy that is greater than or equal to the entropy of the initial state of an isolated system. And equality again holds only if this isolated system undergoes a reversible process. Otherwise, we will always have that entropy of an isolated system is going to increase during an irreversible process. To demonstrate that entropy of an isolated system always increases during an irreversible process, let's consider an example. So in this example, we'll consider a tank that has rigid and adiabatic walls. These walls are well insulated so that there's no external heat transfer to the system and there's no work done on the system by the surroundings. That means this whole system is an isolated system, and initially this tank is partitioned into two chambers, let's say chamber A and chamber B, and it is filled with, let's say, the same gas in chamber A and same gas is filled in chamber B, and the gas in chamber A and B have the same temperature, and you have same amount of mass, let's say mass m, in chamber A and chamber B. But there's a partition that is separating chambers A and B, and this is in a way that, let's say, pressure in chamber A is greater than pressure in chamber B. So PA is greater than PB. If you consider this whole system enclosed within the tank, it's an isolated system. We know that if we remove this partition, then these gases are going to mix and a new equilibrium state will be attained, and we know this from experience. That is, we know that in which direction this system is going to evolve. But let's verify this from the second law so that we can see that when we remove this partition and a new equilibrium state is attained, then the entropy of the system should increase. But to calculate the entropy change, first we need to find the final equilibrium state. And let's consider the gas to be an ideal gas. So what we need is, to identify that final state, we need to have two properties that we need to identify. Those are, let's say, pressure and the temperature. So first, to find that final equilibrium state, we are going to apply the first law. And the first law for this system is straightforward, that the change in internal energy is equal to zero. And that's because this whole system is isolated, there's no work done on the system, and there's no heat transfer to the system. And we know that the temperatures of these two gases initially were equal, and internal energy of an ideal gas is a function of temperature only. Therefore, what this statement says is that the final temperature is going to be same as the initial temperatures of the gas. So there's no temperature change, and that is the conclusion that we draw from applying the first law. Now we can calculate the final pressure. So we know that the total volume is fixed. So let's say volume of chamber A plus volume of chamber B is equal to the total volume. So from the equation of state for an ideal gas, we can calculate the volume. So volume of chamber A is mRT over PA. Volume of chamber B is mRT over PB. And let's say the final pressure is PF, and the final mass of the gas within this tank, the total mass is 2m, and the temperature is fixed. So solving this equation, we get the final pressure PF is equal to, now that we have the final temperature and the final pressure, the final equilibrium state is identified. Now we can calculate the entropy change. Now, although this process is irreversible, we can calculate the entropy change by considering a reversible process that takes the system to the final state from this initial state. So recall that entropy is a property, so we can alternatively, to find the change in the entropy of the system, find some hypothetical reversible process which will take the system from the same state to the same final state. So one way to do this in this example is that we consider a hypothetical reversible process where this partition is quasi-statically moved towards the right, and then what's going to happen is that the pressure in chamber A is going to go down and the pressure in chamber B is going to increase in a way that we attain the final pressure. And during this process, there would be some heat transfer between these two chambers. And once the final state has been attained, final pressure and temperature within these two chambers are same, then we can say that this partition is removed. So we have gone from this initial state to the final state where there is no partition in a reversible manner. And whatever way we take the system from the initial to the final state, the entropy change is going to be the same. And we want to choose this hypothetical reversible process because to know the entropy change, we need to work with a reversible process. So now let's calculate delta S. So delta S would be the entropy chamber A plus that of chamber B. Now we can apply the first law. So for both chambers, the temperature remains constant, so du equals to 0 and dq reversible is equal to pdv, and that's from the first law. So what we have over here is integral pdv over t and similar integral for chamber A going from initial to the final state and chamber B going from initial to the final state. So because we know the final pressures and not the volumes of these chambers, let's change the variables from the volume to pressure, and we can do that because our temperature is constant. That means PV equals to constant. Therefore, PdV plus VdP is equal to 0. So PdV is equal to minus VdP, and also V can be written as RT over P. And we'll also have this mass M because we have this total volume, not the specific volume. So this integral will become this. And if we integrate this, we get minus mr log pf over pa times pf over pb, and that is equal to this. Substituting the expression for the final equilibrium pressure, we can write the change in entropy as this. Now we know that if we have two positive numbers PA and PB, then the sum must always be greater than this. That is, the arithmetic mean is greater than the geometric mean. Therefore, this equation tells us that delta S will always be greater than equal to 0. And when are these two sides equal? Only when PA is equal to PB, and in that case delta S would be 0. That is a trivial case where the pressure of both chambers is equal. So this example shows that the entropy of an isolated system increases during an irreversible process. And note that we have the whole process is adiabatic, and still it is not isentropic because the process is irreversible. Now in this problem, we calculated the change in entropy by considering a specific reversible process which takes the system from initial to the final state. But we couldn't derive a general expression for entropy change of an ideal gas because that expression would be a function of only the initial and the final states, because entropy is a property and it does not depend upon the path, and that general expression we could have used in this problem. So what we'll do is we'll derive a relation for entropy change of an ideal gas. So to derive this relation, let's consider a unit mass of gas. So we can write du is dq minus pdv, but for the reversible process dq is tds, so this is tds minus pdv. Therefore ds is 1 over t du plus pdv. Now du is equal to cv dt, where this specific heat at constant volume is in general a function of temperature. So what we have is we can write this as cv as a function of t over t dt plus p dv over t, and we can write this expression p over t as r over v from the equation of state for an ideal gas. So what we have is cv dt over t plus r dv over v, and now we can integrate this from state 1 to state 2, and this gives us S2 minus S1. Now in general Cv is a function of temperature like this, but if we assume that Cv is constant, that is the gas is calorically perfect, then we can straightforwardly perform this integration and we get Cv log T2 by T1 plus R log V2 by V1. But if the gas is not calorically perfect and Cv is a function of temperature, then this second term would be the same, but we'll have to evaluate this integral differently. So this is the general relation for entropy change of an ideal gas if it goes from state 1 to state 2. And keep in mind that this is the specific entropy. We could have also derived a relation between the change in specific entropy in terms of the initial and the final temperatures and pressures in an alternate way if we use enthalpy. So if we use dH is equal to du plus pdv plus vdp, and that's because H is equal to U plus pv. So du from here we can write as tds minus pdv, and then we have this pdv plus vdp. So these two terms cancel out, so we get dH is equal to tds plus vdp. So Cp dt, that is dH, minus Vdp divided by T is equal to the differential change in the specific entropy. Again, we can perform integration. So if Cp is a function of temperature, then we can evaluate this integral, and Cp is a function of temperature only for an ideal gas, and that we have seen in one of the earlier lectures. But if Cp is constant, we would get Cp log T2 by T1, and this term, I leave it as an exercise for you, would be R log P2 by P1. So using this relation in the previous problem, we could have arrived at this entropy change. All we needed was the initial and the final equilibrium states. And finally, let's just quickly look at entropy change of a solid or a liquid. So for solids and liquids, the PdV term is negligible. Therefore, ds is approximately du by T, and that is equal to the heat capacity times dt over T. And we can integrate this over the initial and the final states. So if you are looking at specific entropy, so we have lowercase s2 minus s1, we can write that as integral of the specific heat capacity C dt over T. So often heat capacity is a function of temperature only, and if we know heat capacity as a function of temperature, we can perform this integration. And for the specific case, that if the heat capacity is a constant, then S2 minus S1 would simply be C log temperature at state 2 over temperature at state 1. So this is the entropy change for a solid or a liquid. So to summarize, what we have done during our discussion for the second law till now is that we've stated first axiomatically the second law in two parts, the first part and the second part. And what we've done is we've given so-called proof of these two parts by reducing these statements to simpler statements, that is the Clausius and the Kelvin-Planck statements, which we have shown are equivalent to each other. But this is not a mathematical proof, because we are just being able to reduce these statements to simpler statements, that is Clausius and Kelvin statements, which do not have any mathematical proof. These are based on empirical evidence.